Hello again, my compadres, or shall I call you my chempadres, I suppose. Welcome back to another week of AP Chemistry Review. This week, we're on to our next big idea, so let's dive right in. We talked about scale and proportion and quantity and structure and properties a couple of times, and today's the day for transformations. Next week, we'll be doing energy and then a final review. And it is worth noting, I suppose, that I'm trying to go through this largely conceptually, right? Just to make sure you have a really good grounding in the ideas that you're supposed to understand. It's going to be really helpful for you at this stage of the game, given that gosh, that chemistry exam's on the 14th, and that's coming up pretty soon. Now's the time to really start, if you're not already in your class, doing lots of practice free response problems from previous years. I try to work a few problems in here and there, but more practice problem solving on your own will be super helpful on test day. So that being said, on to today's new question. The first question, how much stuff is in that stuff? Last time, how to structure influence properties, and we can structure one week and properties the next. Today, it's really all about change. Look at that change, how fast and how far. So those are really two different questions, how fast and how far. And when we talk about change, we really probably mean a chemical reaction. So let's actually start talking about chemical reactions. I'll start with this kind of token cartoon reaction, A plus B goes to C. You've seen it a billion times, right? So one question is, how fast is it happening? How fast are those A and B guys changing into C guys? How fast are the concentrations changing? Another question you might ask is, well, how far do you get? Do all the A and B's turn into C, or do just some of them turn into C? And that's the idea of equilibrium. That's a lot to talk about, and I thought I was going to get through all of it today, but as I started putting this together, I realized that the thermodynamics part is probably going to get snuck into the energy talk next week. So next week will be all about thermodynamics and actually calorimetry and heat and energy, because those kind of all do kind of go together, and I thought I would wrap those up together. But today it's really going to be a deeper dive into the kinetics. But before we start with kinetics, we want to start a little bit more basic than that with chemical equations, right? And I've been taking a lot for granted over the last 3 weeks, but let me talk a little more formally about chemical equations. Here's a chemical equation right there, right? Calcium carbonate goes to calcium oxide plus carbon dioxide. Great. That also happens to be a balanced chemical equation. And what we mean by that is simply it demonstrates conservation of mass, right? The number of calcium atoms on one side of the equation is equal to the number of calcium atoms on the other side. And the same is true for carbon, and the same is true for oxygen. You know, is that always the case? Well, for equations on the AP, yeah, it's kind of always the case. If you have a cool class and a cool chemistry teacher who talks about nuclear chemistry, well, nuclear reactions actually change the identities of the atoms, and that gets to be some super cool stuff. But sadly, is outside the purview of the AP curriculum. So we will be sticking to equations where conservation of mass is always true, so we can always balance these equations. So here's another equation. Nitrogen plus hydrogen goes to ammonia. This is actually an incredibly industrially valuable equation. This is actually how ammonia is made at high temperatures and pressures. So this is happening a lot in chemical processing plants all over the country and world. Is it balanced? Well, no, of course not. It's got 2 nitrogen atoms on the left, so let's take care of that by throwing a 2 in front of the ammonia, right? Now nitrogen's balanced, but hydrogen's kind of a little out of whack. There are 6 on the left, so if we throw a 3 in front of the hydrogen, now there's 6 and everybody's happy. Easy balancing, shouldn't be that big of a deal for you at this point. Let's go through 1 or 2 more super quick. Here we have ammonium nitrate, goes to dinitrogen oxide and water. Worth noting, all that dinitrogen oxide naming stuff, probably not going to be a big deal in the AP because, hey, you've got Google and that kind of thing isn't really going to be valuable this year. So looking at this guy, a little more complicated, right? You know, I would probably start though, like I usually do, by looking for atoms that are only in one place. Right, and here hydrogen is only in one place on the left and one place on the right. Nitrogen gets a little more complicated and oxygen gets more complicated. Oxygen is almost always complicated. So we'll worry about those last. Looking at the hydrogen, I see 4 on the left and 2 on the right, so I simply fix it by doing that. And then if you check, you've kind of solved all the problems because nitrogen's 2 each and oxygen's 3 each, and that was easier than you thought it was going to be. Another reaction that you might recognize is this reaction, and this is what's called combustion of a hydrocarbon. We'll be talking a lot more about this next week when we talk about energy, but any hydrocarbon, add oxygen, you get carbon dioxide and water. Right, so these guys look a little more complicated to balance, but really not that bad because, again, everything's only in one place. Whenever I see an element on its own, like oxygen here, I'm always going to say oxygen, which makes everything else happy. So here we'll start by balancing carbon, 4 on the left, so I'll throw a 4 in front of the carbon dioxide. How about hydrogen? 10 on the left, so I'll throw a 5 here. Now, if I count up oxygens, though, I have an ever so slight problem in that there are currently 13, right? 4 times 2 is 8 plus 5, 13 on the right, but I only have O2 on the left. So can I throw a 13 halves there? Well, not really, but I'm going to because then everything is balanced, but all those numbers need to be whole numbers. So I'm just going to multiply everything by 2, and then I have my answer. Right, so balancing chemical equations should not be a deal for you at this point. So before we dive into kinetics, the AP does cover a little bit about a couple different kinds of equations. So let's start with net ionic equations. So I have a beaker here. We're going to throw in some barium nitrate and some sodium phosphate. Well, that ends up with formulas that look like this: barium nitrate plus sodium phosphate. Well, okay. How do you know what you get? Well, actually, you'd be probably responsible here for being able to execute this, what's called double displacement. You probably learned a lot about different equation types: synthesis, decomposition, single and double replacement. Those aren't really going to be tested explicitly, but you should understand how they work, right? Basically, these partners are going to square dance and switch partners, right? The barium's going to get together with the phosphate and the sodium with the nitrate to look something like this. Something else that you're not going to be super responsible for on the test would be solubility rules, right? So a good chemical equation also has the states. You'll notice that I've got those little AQs and those little S's. AQ means aqueous, right? Those guys are soluble. Those compounds are all dissolved in water. On the other hand, barium phosphate does not dissolve very well in water. That's going to be a solid. So this is actually going to be a precipitation reaction, right? In general, you are not going to be responsible for doing all those crazy exceptions on your solubility rules. And this year, you can just look them up if you need to. So is this guy balanced? Not yet. Let's fix it. I see 3 bariums on the right, so let's add a 3 on the left, but now we've got 3 times 2 or 6 nitrates, and I just think of nitrate kind of as a whole here because it's easier that way. So then I throw a 6 in front of the sodium nitrate. 6 sodiums means I get a 2 in front of here, and oh look, the phosphates check out and we're happy. Great. So that's what's called the molecular equation. In fact, all of the equations on the other page were also called molecular equations because they just dealt in molecules. But when you think about what's actually happening, and it's really nice if our equations can help us understand the actual chemistry that's happening, right? So if you think about the real chemistry that's happening here, it's not terribly well described by this overall molecular equation, because as we said, some of these guys are soluble. So when barium nitrate hits water, poof, dissolves, breaks apart. Same thing is true for all of those aqueous guys. So if we were to write another equation that shows all of those guys dissociating, we get what's called the total ionic equation, right? So I've broken apart barium nitrate, I've broken apart sodium phosphate, and I've broken apart sodium nitrate because they're all soluble. You'll notice, however, barium phosphate, our solid, stays together because it's not soluble. Got it? Cool. And if I kind of just proliferate all the 3s, 2s, and 6s, I end up with a total ionic equation that's also still balanced. The final step here is to realize that there are what are called some spectator ions, right? That is, I've got 6 nitrates on the left and on the right. I've got 6 sodiums on the left and on the right. Those guys aren't really participating in the reaction, so to speak. They're just looking around, which is why we call them spectator ions. So if we remove those guys, we end up with what's called our net ionic equation. And the net ionic equation is just much more helpful to think about, because really, when we talk about mixing barium nitrate and sodium phosphate in a beaker, the reaction that's happening is kind of much better represented, right, by just saying barium plus phosphate gets together to make barium phosphate, because that's what's actually happening. So it's nice to choose the type of equation that actually represents the reaction that is happening. So along those lines, if we really want to get a good understanding of what's happening, we might want to use something called the particulate representation. And this is something the AP has been a big fan of for years and years and years. And that is to instead of thinking of a chemical equation in terms of letters and symbols, to actually draw little pictures, right? So it's not really complicated, but it does kind of help understand what's going where. So if we were to try to draw a particulate representation here, we need to show nitrogen. Great, so let's assume those purple guys are nitrogen atoms, and that's our N2. Well, then we'd have 3 H2s, and those get together to form 2 NH3s, right? So you can see then, literally see, that the same number of nitrogen and hydrogens are on either side, right? So those particulate representations can be handy. Let's go through them quickly for some of the other reactions we looked at. Right here we have a big ionic compound, right, ammonium nitrate, but we're just going to draw it exactly as it appears. And we can see how that leads to the 2 nitrogens now get together with 1 of the oxygens, and I have 2 waters left over. So those particulate representations can be handy to demonstrate your understanding of what species are present and really how much of them are present, right? Because we can also show that, as you'll see in just a moment. So let's imagine a problem or part of a problem that we might see on the AP. So let's again mix barium nitrate and sodium phosphate as we did before, but let's throw some numbers into it. Let's say draw a particulate representation of the ions left in solution after 150 mils of 0.1 molar barium nitrate is combined with 250 mils of 0.05 sodium phosphate. Well, if you recall from a slide or two ago, right, we're going to form that solid barium phosphate. So I better not see any barium phosphate in this picture because I'm asked to represent the ions in solution, and the solid is definitely not that. So the idea, however, though, is that now it's a limiting reactant problem, right? Because how much barium phosphate is formed? Is there going to be some barium left over, or is there going to be some phosphate left over, right? Not hard, but let's throw together the calculation real quick. So to determine that limiting reactant, we're going to start with the barium nitrate. We have 150 mils, and we convert that to moles of barium, since it's 1-to-1, just using the molarity, 0.1 moles per 1 liter of solution, right? And then I imagine how many moles of phosphate we're going to need to react with all that barium. And from our balanced equation on the last slide, we know that the ratio is 2-to-3. So basically that means that we've essentially added enough barium to react with 10 millimoles of phosphate. Awesome. Well, how much phosphate do we have? Well, it's just a simple other calculation. I have 250 mils of sodium phosphate, again, 1-to-1, because there's only 1 phosphate in sodium phosphate. So I just do the simple calculation and find that I have 12.5 millimoles of phosphate. Beautiful. So if I were to try to draw that particulate representation, I'd probably start with one of those phosphates smack in the middle, but I'd probably only write 1, because there's not a whole lot of phosphate left, only 2.5 millimoles, but there's plenty of sodium left, and there's plenty of nitrate left. So you want, when you're drawing these particulate representations, right? You want to show the scale and the concentration by making sure the guys that are there in greater concentrations are just pictured more often in your particulate representation. Not bad. Okay, so we're going to take these particulate representations for a walk a little bit to try to understand a few different types of reactions before we dive into kinetics, right? One of them is acids and bases, right? And I know some of you might be saying, oh, wait, but Aaron, acids and bases aren't on the AP this year. Well, that's true and that's not true. It's true in the sense that that last unit that the AP goes into with buffers and titrations and all that really complicated acid-base chemistry and KAs and KBs and KWs, some of you might be doing that currently in school. Yeah, that's not on the AP. However, I don't want you to totally ignore them because the concept of what the heck is an acid and what the heck is a base, that's actually still fair game. So I just want to go through it real fast just to make sure that you're not totally blowing off acids and bases, because I want you to be prepared for whatever comes at you. So let's start with some water. Let's say we have a beaker of crystal clear, perfectly pure water. And by the way, perfectly pure water is actually hard to come by, right? That is not what comes out of your faucet at home or out of the fancy water bottle that you bought to drink today, right? So really pure water would have to be like reverse osmosis water, deionized in some way, such that there's really nothing dissolved in there but water, just H2O molecules. But not really, because water does this trick, right? Even purest of pure water with no contaminants, those water molecules are going to react with each other to form hydronium ions and hydroxide ions. So in that bottle of water by your side right now to stay hydrated, yeah, there are water molecules, but there are also H3O pluses and OH minuses, hydronium and hydroxide. So if we think about our particulate representation here, I have two water molecules. Over here I have an H3O and an OH minus. Well, what happened? Really, if you think about it, all that happened was a proton was transferred, right? An H plus, which is just a proton. One water molecule donated a proton to its neighbor. Right? And this reaction occurs both ways. So, right, it's forward and reverse. So in the reverse reaction, that H3O plus is donating it right back to an OH minus to make two water molecules. So there's a fancy word for this. Water is what we call amphoteric because it can do this trick, because it can both accept a proton and donate a proton. Right, and this really is what acids and bases are about, right? The only definition of acids and bases, and there are a couple, there's the Arrhenius definition and the Lewis definition. Don't worry about those, they're not on the test this year. But the Bronsted-Lowry definitions are in fact the ones you need to know. And under those definitions, a Bronsted-Lowry acid is simply a proton donor. And a Bronsted-Lowry base is certainly a proton acceptor. So if we look at, for example, this guy, hydrofluoric acid, HF, plus water, right? What happens? Well, look at our particulate representations, HF and water. Again, our HF is our acid, is our proton donor. So it's simply going to donate that proton to the water molecule, which is acting as a base. That forms F minus and H3O plus. But again, this reaction can go backwards, right? So if you imagine the starting on the product side, starting on the right side, going to the left side, right? In that case, H3O would be, the hydronium ion would be donating the proton, and it would be what we call the conjugate acid. And the fluoride ion would be what we call the conjugate base because it's receiving the proton in the reverse reaction, right? So being able to identify acid and conjugate base pairs or base and conjugate acid pairs is definitely something that's fair game on the AP, right? So the conjugate base is just what's left over after the acid gave up its proton. And in the reverse reaction, it's going to act as the base and accept that proton from the conjugate acid, which is what the base used to be before or after it gained a proton. right? So that's HF, hydrofluoric acid, and acid in water. Well, what if we added base to water? This guy's called hydrazine. It is a protonic sep. So when I draw the pictures, that N2H4 and water, well, instead now, water isn't going to receive the proton like it did before, it's going to donate it, right? So now water is acting as our acid and hydrazine is our base. So now we'll have our N2H5, which would be our conjugates, and our OH minus, right? And on the reverse reaction, our now hydrazine plus hydrogen is going to be donating that hydrogen back to hydroxide to form water. All right, so acid-base reactions. Be able to know what they are, know the definitions, identify conjugate pairs, and that should probably hold you through most of it. So moving on to the other type of reaction that I want to talk about today, before we dive into kinetics, this is the last one I promise. Redox reactions. Everybody says redox, short for reduction oxidation or oxidation reduction. So what do those words mean? Well, oxidation is simply the loss of electrons by a chemical species in a reaction. Because as we talked about last time, right? Chemistry is basically just molecules buying and selling electrons. Someone's getting rid of them, someone's acquiring them. So the species, the chemical species, the molecule, ion, atom, whatever, that loses the electrons, we said has been oxidized, and the guy that gains them has been reduced. So in any equation, if there's going to be oxidation, there's going to be a reduction. By the way, not all chemical equations are oxidation reduction. In fact, we already saw one today that wasn't. Most double displacements, actually not redox, right? So let's look at some that actually are. So here are two redox reactions, and one dead giveaway for a redox reaction is if you see a naked element. Right. Here we just have magnesium not bonded to anything on one side in the first reaction and bonded to something on the other in the second reaction. Anytime you see that happening, it's going to be a redox reaction. And we see that in both the examples here. But clearly we should be able to do better than that rule of thumb. So how do we really know if it's a redox reaction? Well, we need a new convention called oxidation numbers, right? So oxidation numbers, sometimes your teacher might call them oxidation states, means the same thing. I'll use them interchangeably as well. The oxidation number just kind of represents the charge state of an atom in a molecule. It's not actually a charge, it's more like a kind of a little theoretical construct we use to help identify where these electrons are going. Right. So there are a couple steps in assigning oxidation numbers that you should be comfortable with. So let's go through those steps and assign the oxidation numbers to the equations that are on the page. Number one, pure elements have an oxidation number of 0. Great, that gets us pretty far. Magnesium, hydrogen, iron, and oxygen there are all in their elemental forms. Sure, some of them are diatomic, but they're still pure elements, so they get an oxidation number of 0. Rule 2, which I probably should have made rule 6 now that I think about it, is that the sum of the oxidation numbers in a molecular ion equals a charge. Clearly, Mg solid is 0, and 0 plus 0 is 0, so we're looking good there. We're going to use rule 2 in a hot second. Rule 3, oxygen is always -2 unless it's bonded to fluorine or hydrogen, and there are the exceptions. Here we do have an oxygen. It's not bonded to fluorine or hydrogen, so each of those 3 oxygens there in Fe2O3 are -2. Okay, hydrogen is +1 unless bonded to a metal. Here there's a hydrogen, we'll make it +1. Group 1 and 2 metals have oxidation numbers of +1 and +2. Okay, I see group 2 metal. Mg +2, great. Then we also have halogens are -1. And that works out perfectly because our chlorine there is -1. And you'll notice that 1 magnesium and 2 chlorines +2 and 2 -1s get me back to 0, obeying rule 2 nice and perfectly. Iron here, however, is still unspoken for, so we actually now need rule 2. How many oxygens were there in Fe2O3, which, by the way, it's ferric oxide, it's rust, right? That second equation is really just rusting. So we have 3 oxygens each at a -2 gets us to -6. So I need to dig out of that hole with a +6 in the form of 2 irons, so they're each +3. So now that we've assigned these oxidation numbers, we can talk more intelligently about what's been oxidized and what's been reduced. So when I talk about oxidation reduction, it's not compounds that are oxidized or reduced, it's elements, right? So in the first reaction, magnesium goes from 0 to +2. Its oxidation number has been increased, so magnesium has been oxidized. Chlorine here doesn't change. So chlorine has neither been oxidized nor reduced. Not everything has to be. But if something has been oxidized, you better believe something's been reduced. In this case, it's the hydrogen, which goes from an oxidation number of +1 to 0. Similarly, in the equation below, we can see that iron is oxidized and oxygen is reduced. You'll notice here both metals are oxidized. That's not a coincidence. Metals typically are going to be oxidized way more easily than they're going to be reduced. Oxygen is almost always reduced as well. Could be oxidized, but that would be a bit of an outlier. When in doubt, we just calculate these oxidation numbers and put it all together. All right, so that allows us to look at these relatively simple reactions and talk about what's being oxidized and what's being reduced. However, there are some really complicated redox reactions out there that actually are really intimidating to deal with. For example, here's a redox reaction that's kind of messy, right? Bromine and permanganate goes to Br2 and manganese ion. Well, you might even be saying, how the heck can I balance that? I don't even see oxygen on both sides. So there is definitely a step sequence for balancing these redox reactions. So it's called the half reaction method. Let's go through it. Step 1, assign some oxidation numbers. Alrighty, we can do that, right? Bromine, -1, because it's an ion, so has to be -1. Oxygen, we always know, is -2. There are 4 of them, but I have to get to a -1 charge, which means manganese is sitting there at +7. Bromine in elemental form, we remember to be 0. And now back to our manganese by itself, but it's not manganese solid, it's an ion, so that means it's +2. So great. So what has been oxidized? Looks like bromine has, went from -1 to 0. What's been reduced? Manganese has, it went from 7 to 2. So we're going to write what we call our half reactions that just show those oxidations and reductions happening, right? Bromine has been oxidized, manganese has been reduced. Okay, so those are our half reactions. Now we have to start balancing those half reactions. Well, for each of them, the first thing I need to do is balance the thing that's actually being oxidized or reduced. In the case of the oxidation step, bromine, I see 2 on one side and 1 on the other, so let's fix that. Great. Now, on the reduction side, it's just fine because I only have 1 manganese of each. Awesome. Next, we're going to balance oxygen using H2O and hydrogen using H+. In the oxidation step, again, bromine, we're good. But now we can see how we're going to solve that problem of having too much oxygen, right? Now I have those 4 oxygens on the left that I can totally balance by throwing 4 waters over there to even out the 4 and 4 oxygens. But now I've created a new problem because I've added 8 hydrogens, but I can solve that problem by doing that. Okay, we're getting closer. Before a chemical equation to really be balanced, it's not just the mass that needs to balance, but also charge. So now finally, I can balance the electrons using my oxidation numbers, right? And here's a nice little check. So bromine went from -1 to 0. So that means 1 electron, right? But there are 2 of them, so I add 2 electrons. Manganese here went from +7 to +2, so that's a total loss of -5, so it must have gained 5 electrons. Awesome. So now I have perfectly balanced half reactions. Great. So now I'm going to need to combine those because electrons are not something that I see in my final chemical reaction. So I need to combine these cleverly so that the electrons all cancel out. In order for that to happen, I'm going to need to multiply the first reaction by 5 and the second by 2. Why? Because when I put it all together then, multiplying everything by 5, everything by 2, and simply adding, you'll see that I have 10 electrons on either side of the reaction. That's great. It allows me to simplify and just be left with this balanced reaction. So I submit to you that it would be really hard for you to have come up with that answer as a balanced chemical reaction by just looking at this redox reaction and trying to do it in your head, right? So this half reaction method is definitely what we should use if we see unbalanced hydrogens or oxygens, or if we see a lot of charges running around and we suspect it might be redox. Yes, so we went from our initial reaction to our balanced reaction. But to kind of tie this together with acids and bases from a hot second ago, you'll notice some H pluses running around. That means that this is a very acidic solution. But what if it were in a basic solution rather than acidic? So sometimes you'll be told to balance this in acidic solution or balance it in basic, or just have enough context in the problem to know. Well, there's a little trick for balancing redox and bases. And the trick is you just do it in acids first, and we get our answer. But then we can make this into a basic solution rather than an acidic solution by solving our problem. Our problem is that I have 16 H pluses, right? Well, what I'm going to do is I'm going to add 16 OH minuses to both sides of the equation. Why am I going to do that? Because what did we say happened? Hydrogen or hydronium and hydroxide get together to form water. So I can combine those to form water. I still have my 16 OH minuses on the other side, but I also have 8 waters on the other side. So now those 8 waters are going to cancel to leave me with my final balanced basic equation, which will have 8 waters on the left and hydroxide on the right. So I basically replaced my my acidic hydronium ions with my basic hydroxide ions, right? So, you know, fairly complicated process in that there are a lot of steps, but it's not like any of the steps are super hard themselves, right? So if you're comfortable with the process, it should be fine. All right, as promised, after we've dealt with a couple of different kinds of reactions, let's actually dive in and talk kinetics a little bit. So how fast do reactions happen? Well, let's imagine a reaction, a real one, not an ABC one this time. Nitrogen plus hydrogen goes to ammonia. We saw that already. So if we imagine just looking at how the concentrations change over time, let's say in our reaction vessel, we start with a bunch of nitrogen and a bunch of hydrogen, and we end up with some NH3 and some nitrogen and some hydrogen left at the once this guy's reached what we call equilibrium, right? Equilibrium is just when the concentrations aren't changing anymore. We'll talk more about how to find exactly where that equilibrium is next week when we talk about thermodynamics a little more in detail. But for now, great. So how will we talk about how fast this reaction is? Well, we need what's called the reaction rate, right? And the reaction rate just measures the speed of a chemical reaction. And the units of a reaction rate are always molarity per time, right? Usually moles per liter per second, right? How many moles per liter per second are being gained or taken away? And that brings us to an interesting question, because how do we even talk about the reaction rate of a reaction when all of the different components, right, all the different molecules are changing their concentrations at different rates themselves, right? Because if we say that this reaction rate is molarity or concentration per time, well, cool. So if I imagine a slope right here to start, you'll see that slope would be like the value of the reaction rate. But at the same time, I can the slope is also totally different, but they are related, right? Why? Well, as it turns out, the slope of hydrogen there is steeper than nitrogen, right? Turns out to be exactly 3 times as steep. Why? Because of the coefficient 3. Every 1 nitrogen molecule lost takes 3 hydrogens with it, right? So the slopes are different, but they are related, which is how we can write one reaction rate, right? So how that works, and let me go back to a toy reaction, AAs and BBs get me CCs, which is how you usually see it presented in textbooks. So the reaction rate that we're going to be talking about a lot, R, the rate, is really the change in species per time divided by its stoichiometric coefficient. Right, and if I do that, then that gets me the one true same reaction rate, no matter which species I happen to be looking at. Got it? Cool. So how do we find the reaction rate? Or how do we express it? Or how do we think about what makes a reaction faster? Well, typically there are a handful of ways that you can make a reaction faster. One, we can increase the concentration. right? And we'll talk in a little more in detail in a moment about why that works, but surely if I add more stuff, then more of it will react faster. I can also increase the temperature. Right, making things hotter generally increases the reaction rate, right? You make coffee with water and not cold water. We can also increase the surface area of the reaction, right? This one you don't think about so much and is a little harder to apply, but I'll just say, imagine going on a picnic on a hot summer day, right? Let's put some ice in a cooler. Well, if we put some ice in the cooler, what's going to melt faster, a big 5-pound block of ice or a 5-pound bag of ice? If you have any experience with coolers and ice and picnics, you know that the block of ice stays icy way longer. Why? Because ice doesn't melt from the inside, it melts from the outside. So it's a surface area argument, right? A bag of ice has more little ice chips that are exposed to the air to a much greater degree than that big block of ice. And chemical reactions happen the same way. So the more I can mix things up, right? And this is why pretty much you stir everything that you cook, right? You're trying to put molecules in contact with other molecules and increase the surface area so that things happen faster, right? And then finally, you can add a catalyst, which we'll talk about later. But really, so all of that kind of is related to what we call the reaction rate law, the equation that we use to express the reaction rate. And the rate law kind of looks like this for our reaction A plus B goes to C. It equals K, which is the thing we call the rate constant, times the concentrations of the reactants, not the products, but the reactants, raised to some power. And that power is what's called the order of the reaction, all right? So this is X order with respect to A and Y order with respect to B. The total order of the reaction would be X plus Y. And it can be compelling to think to yourself, oh, I'm just going to use those stoichiometric coefficients to pop in from X and Y's, but that is not always true. In fact, we actually can't determine the X and the Y or the K by looking at a chemical reaction. And it's really insanely hard to do by modeling. Some would say even impossible. So what choice do we have? All we can do is do experiments, right? So being able to look at some experimental data to determine what these rate laws are is definitely something you should be able to do. Most of these are going to look like what we call initial rate calculations. So let's look at a token problem like this that we might see on an AP, right? Calculate the rate law for this reaction. So we have 2 nitrous oxide plus chlorine goes to 2 NOCl. We want to calculate the rate law for that reaction based on the data below. So what I have here is I've got 3 trials, trial 1, 2, and 3, with different initial nitrous oxide and different initial chlorine concentrations. And they've measured the initial rate of chlorine disappearance, which in this case would in fact be the rate of reaction R, because the stoichiometric coefficient of chlorine is 1, so it's basically R. So how to navigate this, right? So basically you could also think of it as like the initial slope on that graph that we looked at. First we need to write our rate law, right? R equals K. Now we have the reactants, so NO to the X and Cl to the Y. So job 1, find X and Y. And we're going to do that by looking at some concentrations, right? So if I just look at the first 2 rows, if we double the concentration of NO, what happened to our rate? It didn't double, actually went up by a factor of 4, right? And 4 is 2 squared, so that's how we know that X has to be 2. On the other hand, if you look at this, the last 2 rows, where NO is staying the same and I'm doubling chlorine, you'll find that that actually just does double the rate. We're calculating K, and it's really not that bad. As I had mentioned, the units of K can actually change depending on the order of the reaction. So K always changes its units to make sure that R, the reaction rate, has that same units of molarity per time. Cool. So that's one form of the rate law. There's another form called the integrated rate law, which is important. So now if we think about just a little baby reaction, A goes to B, and I look at the concentration versus time, if it's 0th, 1st, or 2nd order, we get some different graphs, right? So if we want to, and this is a graph you could imagine that you would get a lot, right? It's something that a chemist might be curious about. What's the concentration after 10 minutes, after 20 minutes, after 30 minutes? Super important stuff there. So how can we use whether a reaction is 0th, 1st, or 2nd order, which now we know how to calculate? How can we use that information to help us predict something about concentrations and times, right? And that's using what's called the integrated rate law. Right. So we need some new equations to deal with that. Worth noting here that the zeroth order reaction, right, that's where the rate doesn't depend on the concentration, which might seem a little weird to you. Right, and that would be a constant straight line on a concentration time curve, right? First order reactions look more like exponential. Second order decrease actually even a little faster than that. So how can we use the information that we have once we know what order a reaction is by problems like the last one? How can we use that to move forward and make progress? Well, in your chemistry book, I am sure there is a big table that looks like this, filled with integrated rate law expressions, right? This is something I would definitely bookmark if I were you, because you might be referring to it during the AP exam to make it easy to find, right? So what those rate law expressions look like for zeroth, first, and second order, because that's just the exponent of concentration. Then we have integrated rate laws, right? Were this a calculus class, I would be ever so delighted to derive them for you. However, it's not. So we're just going to take them on faith. And again, they're in your book, bookmark the table. Right. Something that does come up, though, is we said that a zeroth order reaction, when we plot concentration versus time, we get a straight line. Right, and the slope of that straight line is actually minus k. So that's another way to determine a rate constant, right? If you plotted concentration versus time and got a straight line, you could literally fit a straight line, find the slope, and that would be the opposite or negative of your rate constant. That's super handy. It will be great to do that for first and second order reactions too, and we can. We just have to plot them slightly differently. For first order, we plot the log of the concentration versus time, and for second order, we plot 1 over the concentration versus time. It wouldn't shock me if we see questions on the exam about how to linearize these guys. So if you see data where it's the log of the concentration plotted, that's going to be a first order reaction. If you see data where the inverse of the concentration is plotted, that's likely to be a second order reaction. Another really important way to distinguish is what we call the half-life, right? The time it takes for half of the reactants to turn into products, right? Something that the AP just loves to test on is that first order reactions are the only ones with constant half-lives, right? The half-life for first order reaction there is just 0.693 divided by the rate constant, right? The others for zeroth or second or any other order for that matter are going to depend on how much you have on the initial concentration. So first order reaction, the half-life stays constant. So I could totally see them sneaking in information about that constant half-life and needing you to realize that means it's a first order reaction. Why is that the case? Well, if you think about half-lives, right? If I start with a higher concentration, well, first order reaction is faster. If I double the concentration, well, it's twice as fast. So you get rid of, half of the amount, whether it's a larger amount or small amount, in the same amount of time, right? The zeroth order reaction, you'll see that the half-life is decreasing with decreasing concentration. Why? Because or increasing with increasing concentration, if you will, for zeroth order, because the more you have, the longer it's going to take to get rid of because the rate is constant, right? Opposite for second order. Cool. So a couple more things. An elementary reaction or an elementary step. So an elementary reaction is a single step reaction that has one transition state and no intermediates. We're going to talk about the words transition states and intermediates in a moment. It's kind of a what you see is what you get reaction, right? And in those cases, we actually can write a rate law directly. It's worth noting that these have to be unimolecular or bimolecular, right? That means 1 or 2 molecules. So if I were to write this chemical reaction, that is not an elementary step. One way you know it is because there are 3 molecules on the left side, right? And it is not the case that like 2 nitrous oxides combine with 1 chlorine and they all like smash together at exactly the same time to produce 2 NOCls. That's just not how it happens, right? 3 body collisions aren't very, very probable, right? What is, however, an elementary step would be something that looks like this. Hey, 1 nitrous oxide and another nitrous oxide come together and form N2O2. Great. How will you know it's an elementary step? Generally, they're just going to tell you, right? So what it means, though, if it is an elementary step, that means that yeah, it looks exactly like it is. so when these two collide, is it the case that every time two nitrous oxides collide, you form N2O2? It's actually not, right? You know, in order to react, yeah, I mean, a collision is required, right? They have to be in the same place at the same time to react, but not all collisions will form reactions, right? First of all, you need to have enough energy, right? These guys need to smack together hard enough to have enough energy to actually react. And in some cases, right, the orientation needs to be right? If you were to draw a Lewis structure for N2O2, which you should totally be able to do after last week, right, you'd find out that nitrogens are in the middle. Right. So it's the nitrogens that are bonded together that hold those two NOs together, if you will. So if they kind of those two NOs collide from the oxygen-oxygen side, it's going to be much harder for them to react than if they collide from the nitrogen-nitrogen side, right? So there are some details there. So let's think about how we can kind of model those details. In this case, let's consider a different elementary reaction, N2O2. The product of the last one, plus Cl2 goes to 2NOCl. So if we look at what we call an energy profile, right, we're kind of here plotting energy versus this thing that's very obliquely called reaction coordinate. Basically, reaction coordinate just is the progress of the reaction. From left to right, I'm going from reactants to products, right? So if I look at an energy profile, it often looks something like this, right? Where the reactants are sitting there on the left, the products on the right, and in the middle is what we call an activated complex or a transition state, right? So for this case, what are my reactants? Well, I've got N2O2 and Cl2. What are my products? Well, I've got 2 NOCls. Well, my activated complex is kind of like, or transition state, it's kind of transition state's kind of old language, but you're still going to see it a lot. So that's kind of like where the reaction is just on the precipice of occurring, right? So here you might imagine it could look maybe something like this, right? You can imagine that chlorine molecule kind of nestling in there with the N2O2, and the kind of bonds between the chlorines and the oxygens are starting to form, and the bonds between the nitrogens and the chlorines are starting to break. Everything's kind of bound together and kind of not, right? Such that it's kind of like balancing exactly, it's pictured here, right? If you were to balance a ball on the top of a hill, right? Half the time it's going to roll left, half the time it's going to roll right. It's like that very unstable point. And that's what this kind of activated complex is, where half of the time it's going to go back to form reactants and half the time it's going to form products, right? But what's worth noting here is that that's a higher energy state, right? Not all the bonds are formed, and we said that bond formation, we said last time, is a good thing, right? Because generally forming bonds lowers energy. So in the activated complex, really none of the bonds are fully formed, so it tends to be a higher energy state, right? So how much higher that activated complex energy is compared to the energy of the reactants themselves, and we'll talk more about how to find those numbers next week when we talk about energy, is what's called the activation energy, right? And that's why not all collisions result in reactions, right? They need to overcome that energy barrier. They need to have enough energy to overcome the activation energy to kind of be able to get down the hill to the other side and form products. All right, so if we think about this, we talked about the Maxwell-Boltzmann distribution last time. So let's revisit that for a hot second. And if we think about what the activation energy might be and say that's the line that's activation energy. Well, clearly my red curve here, more than half of those molecules have enough energy to probably collide and react. On the other hand, at 1,000 Kelvin, right, very few of those molecules are going to be higher energy than that. So the Maxwell-Boltzmann curve can help us understand why it is the case that the higher the temperature, the greater fraction of collisions give rise to reactions, right? And this is encapsulated in something that, again, is not going to be tested on the AP. This what I'm showing you now is what's called the Arrhenius equation. It's actually an equation to calculate that rate constant. And that's really where the activation energy and temperature come into play. However, the AP has made a decision not to test on this, so I'm not going to go in detail. But if we think about what we talked about in terms of how to make a reaction faster, right, I can increase concentration because that will just give me more collisions, right? Or I can increase temperature because that means that a greater fraction of those collisions would result in reactions. Or I said we could add a catalyst. What does a catalyst do? That just simply lowers the activation energy required so that a greater number actually collide. All right, and I wanted to end today on a note about reaction mechanisms. And if you've been paying close attention, all the examples I used today kind of led to a reaction mechanism. So the mechanism really is just a series of elementary steps, and we said the elementary steps are the ones that are what you see is what you get, a series of elementary steps that combine to explain a multi-step reaction. So in this case, the example I used that was not an elementary step looks something like this, right? NO and Cl2 go to 2NoCl. And we said it was not the case that those three guys smashed together. But if you were paying attention, you noticed that I gave two other elementary reactions in the last couple of slides. The first one, two NOs get together to form an N2O2, and then an N2O2 collides with a chlorine to produce 2NoCl. And these I'm going to say are step 1 and step 2 of my mechanism. And you'll notice that if I add them together, right, the N2O2 is formed and then immediately broken apart, right? So if I add them together, I get my overall reaction, and N2O2 doesn't appear in it at all. That's what's called an intermediate. Right. So great. So clearly, in order to be a valid mechanism, the steps better add up to give the overall reaction. But this was also the example I used to find the rate. Right. And if you recall, the rate was second order in NO and first order in chlorine. So our mechanism should be able to explain that as well. Right, so let's walk through the process by which we can check to see if in fact it is consistent with the data. So in order to do that, I need to add one more little bit to my mechanism, and that is the idea that step 1 is going to be what we call the fast step, and step 2 is going to be the slow step. Right, so when I want to write the rate of the overall reaction, right, well, that's going to be determined by the slowest step, right? It's the bottleneck. It's what they call the rate determining step. So here it's going to be step 2. So if I write the rate law for step 2, which I can because it's an elementary step, I'll have something like this. Okay, cool, but this is a problem because N2O2, not a reactant or a product. So we need to do something about that. And what we're going to do, and we're going to talk more about equilibrium next time, so preview here, we're going to assume that that first step is actually in equilibrium. That is, the second step is so slow that the first one can sort out its business happily before the second one ever acts. So that would mean that the forward and reverse rate of that first step happen to be equal. Right, so I can set up an equation to actually solve for the concentration of that intermediate. And if I do that and substitute it in, I actually get something that agrees with the data, right? That this mechanism is consistent with the idea that we saw in the data. That is that nitrous oxide was second order and chlorine was first order. So does that tell us our mechanism is right? No, but it tells us it's not wrong, which is good. So being able to test and see is a mechanism consistent with the data is something that you definitely want to be able to do for the AP exam. Alrighty, so sadly, that draws us to a close today. It's been about an hour, but I look forward to spending one more content week with you guys, where next week we'll talk all about energy and equilibrium and some ICE tables and Q equals MCAT calculations. So a little more calculational rather than conceptual next week. And then our final week before the AP exam is just going to be problems. It's just going to be me reaching for my crystal ball and trying to predict exactly what kind of problems I think are going to come up. So I'm sure you'll want to be there for that one. Thank you so much for your time and attention, and I look forward to seeing you guys all next week. Take care.